my background is basically Maxwell demonology. And, I've been curious about machine learning and how things actually learn for a long time. But, now we're faced with this question of what AI can do and what AI will be. So, to answer this question, I think it's important to sort of think about the space that these AIs could possibly realize. Like, what could happen? There's some spectrum of different outcomes, somewhere from the AIs being kind of smart and being like gods to us. Masters of our fate, masters of the fate of the universe. And then there's another question. Are they malevolent or benevolent? And I imagine we each have our own priors on this sort of question. Just for context to what we might imagine in these quadrants, you could imagine, Roomba as a kind of smart, benevolent thing. It's going around doing useful things for us, using some limited intelligence, cleaning up the floor, for instance. It's amplifying our lives in some small way, but it's not transformative. I mean, we can pretty much sweep the floor ourselves or vacuum the floor ourselves. Or, we could have an evil Roomba, that makes life mildly inconvenient, chasing us around with a knife or something, but ultimately it's not an existential threat. Or maybe what we're doing by pursuing AI in this way is we're basically creating the robot devil. A super intelligent being whose intent is to harvest our energy and our attention and basically, suck our souls. Or maybe the ideal outcome is something, a benevolent entity that's able to truly help us amplify our lives in ways that we can't possibly imagine. Amplify the environment, create new space for creativity, for new ways of human life. So these are all, we may all have some expectation that lies somewhere in here. And I would like us to do that was the wrong slide. A quick poll. And I will give you the QR code, so maybe if you hold up your phone. This is terribly small.
Yeah.
Okay, I'll just put the
Can you just
If you do like
Command plus.
yeah,
command plus.
Yeah, they should.
several times.
Command plus. Nope.
Can you just split full screen that?
Yeah.
That
Yeah.
matters.
Great.
There we go.
Oh, there we go. That works perfectly. All right. Sorry for the delay. So I would appreciate it if everyone would fill out a quick survey about whether you strongly disagree or agree or somewhere in the middle with these claims. And I'd be curious to see sort of
Is there a
what
time scale for these questions?
Yeah, that's what I was asked to, yeah.
Is this like 10 years?
It's heavily time dependent.
Yeah.
well, let's just say infinite times.
Infinite times.
Yeah.
Okay, 10 years. In 10
10
years.
years.
In 10 years.
What does it mean to solve the human brain? I don't know the question.
Okay.
It's up for interpretation. It's up for interpretation. Let's say 10 years.
10 years,
Yeah, you
okay.
can go to menti.com and use that code.
Oh.
So the QR code, if you scan that, will.
What if it's like,
Pardon me.
wait, but what these aren't like probabilities, are they? It's supposed to be like,
So whether you agree or disagree with what will happen.
Within
Possible.
10 years.
but like,
Possibilities.
but like agree or disagree. It's like I think it's a chance some of these things could happen.
Right.
But does that mean I agree or disagree with them?
Sounds
I
like,
think-
sounds like you
Like if it's
turn it
if I
up.
think it's a 6% chance, does that mean I agree with the statement? Or I think it's a 30% chance. Does that mean I disagree?
I'd say, let's say 50 and above means, I mean,
Just map it
about
to.
50-50, 25, somewhere between like 15 and
10 years.
I see. So just map probabilities to agree, disagree.
Yeah, I
don't
don't
know what
know.
that's doing.
like something like that. Course grade here.
That's what I'm-
Okay, here, this is
I'm
interesting.
still trying to work my grid.
All right.
I'm still trying to get the top of this stuff coming up on faster than light. 10 years is soon.
Okay.
No, 10 years.
Oh,
Oh,
this
but people are like, the singularity, it's just around the corner.
Yeah, next week.
Yeah,
Yeah,
next
I heard-
week.
Oh,
That's
with the
what
new
was
book,
going
The
on.
Singularity
Like,
is
in
Near
this
Us.
building.
Well,
They had a big cross on it. They were like, every 10 years. 10 years.
Hey.
Writing this book.
Kurzweil will, every 10 years will update his prediction.
Are we in the singularity?
I guess you already know half of it.
Seemed like that in the middle of this one.
Sure, most people think we are.
There we go.
So, if anybody's still working on it, maybe let me know. Nobody? Okay, it seems like we have full participation.
You've turned me into a pessimist.
I've turned you into a pessimist. All right. Well, it seems as if I'm actually surprised by the degree of agreement here. It seems like we have some pretty strong agreement that AI will, in 10 years, drive cars better than people. I mean, that seems reasonable. Solve climate change. This seems to have a wide spectrum of outcomes here.
It feels like it's a more political issue than a.
That's part of it.
Well,
It's a
right.
part of it.
It's a political issue, right?
Yeah.
But can the AI navigate politics?
We
Right?
could elect AI.
We could elect an AI,
wow.
and then
Might be better than the current option.
I agree.
Some people thought that in 10 years, an AI may likely build a Dyson sphere around the sun. That's interesting to me. It's that's a non-negligible.
That's a heavy lift.
It's a heavy lift, but not impossible. Some people also seem to think it may solve the human brain. Nobody really seems to think we communicate faster than light. That's
This is physics here. Physics of stars.
yeah,
I think I put a disagree rather than strongly disagree because
yeah.
Yeah.
I'm like, well, we don't know all the things.
If you had to
10
bet
years.
though, what you should have asked is how much money would you bet?
Yeah.
Yeah, how much
If
money?
you want to get a really accurate.
Right.
Well,
The
the
Kelly
dollar
criterion.
amount,
I want
how
you
much
all
you
to
would
apply the Kelly criterion right now.
How much
Predict-
retirement would you invest?
How much of your
Well, the thing is, some of these makes money relevant, so like,
Yeah.
better more.
Yeah.
Yeah, right.
Some people actually seem to think that you could predict the weather 100 years into the future. This is interesting to me. To me, this seems like the least likely one.
I guess like something
The least likely.
Yeah.
That's
I
I mean, I'm not gonna
Less
say
likely
Crazy
than
idea.
communicating faster than light.
What?
Less likely than communicating faster than light.
Yeah.
The Dyson sphere is so unlikely. Just to travel to the other side of the sun is going to take a little time.
But does it
Let's-
Think of the amount of
Dyson-
material. Think of the amount of material it
Yeah.
would
If
take.
they were already
What
starting now, it'd still
manufacturing
take
thing
longer
would
than 10
make
years.
it faster?
I don't think so. You have like nanobots or something. I think Dyson sphere is like out of those three, it's the most reasonable.
Out of these three.
Could it get faster than light, predict the weather 100 years in the future, and Dyson sphere? I think Dyson sphere is the most reasonable.
One of them is
That might be
This is
true.
also
Yeah, exactly.
Feel like
build an engine that turns heat directly into work.
I thought people would be more optimistic about that.
Really?
well, there's got to be a loophole somewhere.
Absolutely.
You think there's a
The
loophole?
fact that we exist implies there's a loophole in the law of physics somewhere.
no, I don't think that's
We
true.
start a universe with a very low entropy.
I've broken the law.
That's kind of our argument.
Okay. Interesting.
Yeah.
Yeah. I strongly agree. Someone was strongly agree on that.
Yeah.
I guess we're not anonymous.
The last 15 years. I mean,
Yeah.
In 10 years.
I guess I have a slightly different perspective on that. But okay,
Well, you didn't say what the assumptions were.
with the assumption existing in our universe, I thought was an assumption. But yeah,
Faster than light.
Initial correlations.
we'll see. We'll see.
It's an optimistic group.
I like it. I like the optimism. So, I guess my point with that would be there's a spectrum of opinions. Maybe there's some interesting alignment that we have on what to expect. But for these wild claims, there's sort of like a wide array of different things we might predict. And at the end of the day, we should really have a more scientific framing for why we believe one outcome is more likely than the other. And maybe that's just our point, is with the physics of intelligence, we would hope that we can more strongly bound the probability of these outcomes, or even the possibility of these outcomes. And, you know, I'm talking about the thermodynamics of intelligence because why does thermodynamics matter? Well, historically, in the last time we had a revolution that felt like this, to me, is when we had the Industrial Revolution, and suddenly we discovered we no longer needed to use human labor to do useful work. We could use chemical energy. And we could use chemical energy to, say, rather than ride a horse, take a train wherever we need to go. And as people start to build these engines, as people, you know, are like, if I put this gear next to this piston and tie these things together, kind of like the way that you tie together layers of transformers, you can do more and more. And if we just do this ad infinitum, maybe we can build a perpetual motion machine. Maybe we can, you know, this here depicts a water wheel that is simultaneously being driven by water and pumping water up. And through that, you know, basically creating motion without any input. And what thermodynamics revealed through the first and second law is that perpetual motion machines are impossible. You know, this basically... Asymptotically. Okay. Perpetual. Yeah. Yeah. Energy conservation is a thing. This is a rule of the universe, as far as we can tell.
Given two assumptions.
And lots of observations.
Sorry, given what? Sorry, what assumptions?
Like initial non-correlation between system and environment, and
Energy conservation.
things like this. Oh, that's not what I had in mind.
But entropy increased. The second law, given two assumptions.
Yeah.
Okay, right. Paul has a beautiful paper that you can look at for deriving the second law of thermodynamics from Hamiltonian dynamics. So a type 2 perpetual motion machine is something that, you know, transforms heat energy into work energy and basically diminishes the entropy of the universe. So,
Can I make one comment on the drawing too?
yeah.
It's interesting is that it's disturbing to look at that and I realize, it's because the perspective's wrong. The artist doesn't, like it's violating, it's violating various laws, you know, both in terms of projection geometry as well.
Yeah.
Like think of the top, you're looking up at that thing, even though just beneath it, we're looking down at that.
So if we have hyperbolic geometry, would we be able to violate energy conservation?
And it's an Escher-esque, you know, like in the Escher picture where you've got where you have the ascending staircase, they're always, it's the same where they're breaking rules, but he's doing it intentionally. This guy just doesn't know. He doesn't know perspective.
Doesn't know what he's doing.
But it's a funny,
Yeah.
it's a nice, anyway, sorry.
Yeah, no, it's good. That's a great comment. It's interesting. So beyond conservation of energy, yes, there's also the constraint that entropy is non-decreasing, and that tells us that you have things like the Carnot efficiency and Carnot cycles, which achieve the Carnot efficiency. So in this context, can we figure out something like the Carnot intelligence, the thing that makes maximal resources or use of available resources to do something functional and intelligent? Does that even make sense? Like, you know, is there a measure that we might use, like work production or efficiency for intelligent engines? Well, I argue that thermodynamics actually does lead to principles of intelligence. And what I'll try to do is go through sort of a series of results here and then basically go to the point where I'm like, I don't really know what to do, and yeah, we'll go from there. So, as I mentioned, my background is a Maxwell's demonologist. You know, Maxwell's demon is basically one of the first places physicists began to think about intelligence in terms of its paradoxical impact on a box of gas, where it's harnessing thermal motion to do work through intelligent feedback. And this can be very easily seen through a Szilard engine, which is a 1-bit Maxwellian demon where you have, you know, a box with a single particle in it, and then you insert a barrier, and the demon has a memory. By the way, Kyle, I stole this from you. He has a wonderful paper with Jim about basically how to experimentally implement a Maxwell's demon. You should check it out. So you can do a measurement step where you put a barrier in between, separate the particle into either side, and then the demon's memory becomes either a 0 or a 1. This is very familiar to some of you, maybe not to all of you. So basically, the demon is storing where the particle is, and then based on that memory, it has feedback, it has an action policy that it then uses to extract work by expanding the barrier away from the particle. And then it resets. And so this introduced a paradox in that you're just turning the thermal motion of the particle into useful work, and, you know, violating the second law of thermodynamics. The total entropy of the world is decreasing in this case. And the way of realizing that, or resolving this paradox, is not to imagine you have the ability to just randomly or just arbitrarily measure and feedback on an environment, that information processing itself has a physical instantiation, that the demon's memory is something that is being controlled in tandem with the system that's being measured, the 0 and the 1 state for the particle. So you're doing some sort of chaotic mapping, transformation of the joint state space of the mind and the system together. And this sort of resolves the paradox altogether in most cases. So this is basically a consequence of, you know, the idea that information itself is physical. And in the same way, we should realize that intelligence is physical. Intelligence is bounded by thermodynamic law. And so, you know, we have these rules that entropy is not decreasing, we keep production. This is Landauer's bound, basically. Any reduction in the state space of a computation that you're doing must correspond to heat production in the environment. And this is because, you know, basically our memories are these metastable systems that store particles, and then the energetic control of them through, you know, Hamiltonian landscape guides the way that they evolve, and this requires impulses of energy. So this field is basically the thermodynamics of information. And it tells us that information quantities, information diagrams, have physical consequences. So there are these diagrams that are basically Venn diagrams between different pieces of a physical system. So in this case, you know, you have maybe some past, some future, and some demon, all representing some piece of your system. And their joint entropy is the whole area of all these information diagrams. And then you can look at things like the information shared between the past and the memory of the demon, which would be this wedge here. And there's a pretty simple you know, algebra for this. You can just add the information atoms up to evaluate what pieces you want to calculate. So you can build it up from marginal distributions and joint distributions. And from this, we get a series of results that relate thermodynamics to complexity. For one thing, if you look at, say, a process of transforming information from inputs to outputs, the work rate that you get out is upper bounded by KT, which is the thermal energy scale of that system, times the entropy rate of the output minus the entropy rate of the input. And these entropy rates is just a fundamental irreducible uncertainty in the system. You can also show that there's an irreducible heat required for synchronizing to a process. And that's greater than or equal to the information shared between the past and the future of that process. So here, the past and the future share this information bubble, which is known as the excess entropy. And that captures some amount of correlation structure in the process. It's a lot like complexity. And in addition to that, we also can show that there's a principle of thermodynamic requisite complexity for efficient information harvesters, things that harness energy from information. And basically the mind of the daemon, the entropy of it, must exceed the statistical complexity of the process itself, which is basically the size of the minimal partition of the past that fully predicts the future. So basically, the daemon's mind must contain all relevant predicted features of the process it's interacting with to extract energy with it, which is maybe understand or intuitive, but it's nice that you can directly prove this from thermodynamic principles. So basically what this comes down to is that there are two thermodynamic conditions. One is thermodynamic efficiency, that basically says the mutual information between the past and the future conditioned on the daemon is equal to 0. And the condition of causality that basically says that any dependence the daemon has on the future beyond that of the past is 0. So basically the daemon's mind, can be correlated with the future, but only in the degree to which that future is determined by the past. So prediction is actually a provable phenomenon in the context of thermodynamics.
Does that, it sounds like your daemon has to have phenomenal capacity, right? You could have arbitrarily high correlation between information between the future and the past, right?
You could, yeah. You could have fractal mixed states, for instance, and you can actually have pretty simple processes generate fractal mixed states for which this entropy would be infinite.
So you'd have to have he or she, your daemon, and have to have an infinite amount of memory
Indeed, yeah.
To meet this efficiency.
for it to give that great efficiency.
Yeah, but I mean, at some point maybe you're like, I will tolerate, 1/1000th of a KT inefficiency for getting that much information about the past. And I think we often,
And you also have to shift the mathematical foundation. With these quantities going infinite, then you can't use them directly. Even if they're growth rates, they're scaling kind of statements.
yeah.
Right?
How much more information do you need from the environment to stay synced up to it? It's more like a process picture.
Thanks.
Yeah, that's a good question. So with this knowledge, you can basically set up a thermodynamic system for machine learning. Thermodynamic machine learning through maximum work production, which is basically the idea that, okay, if you have some data, you can take a bunch of information engines, a bunch of daemons, and have each of them harvest as much work as it can from that data. And you look at the agent that produced the most work, and you call this your maximum work agent. And you think, this is my best daemon. This has the best model of the world, this has the best model of the data. And what you can show is that this is, that's the wrong direction. This is equivalent to something, or to a common form of density estimation known as maximum likelihood estimation. So, the physical system that the daemon's interacting with, the harness energy, is basically formally equivalent to data. The daemon, in the way that it interacts with that data, it has memory states, and it has predictions based on those memory states of what it will see. The way that the daemon operates is formally equivalent to something known as an epsilon machine. It is, if you have a predictive model of the data, then you know exactly how to design your daemon to harvest energy. And on top of that, the work production from the daemon is linearly related to the log likelihood of the performance of this epsilon machine on the data. Meaning that this process is simply maximum likelihood estimation. Finding the maximum work is simply maximizing the likelihood. So we're doing an interesting format here. We'll see how it works. Now is a moment to have about 5 minutes of questions clarifying, anything that you think needs more explanation in the talk. I just want to open the.
At some point you said that you can explain almost all the variations per second look from the maximum daemon perspective, that information is physical.
Yeah.
Why did you say almost all other cases why this doesn't work?
Well, I think that I'd say there are very many, maybe I misspoke in saying almost all. I'd say there are many things that you can explain through a thermodynamic perspective. There just hasn't been that much work exploring the way that thermodynamics implies forms of machine learning, forms of complexity.
Yeah, some of these nice summaries of the results are for particular cases. And
Yeah.
so if this infinite memory case comes up, and that's,
Yeah.
we need to work on that more. So,
Yeah.
so there'll be cases that the simple, nice summary doesn't quite work. You have to think about the rate of divergence of the demons measured to stay synchronized. And so,
Yeah.
But modulo that kind of complicated stuff.
Yeah.
Results are
How are you feeling about this thermodynamic machine learning process, I guess? Any discomfort with it?
My only discomfort is, again, definition of, I guess, if it's phrased in terms of intelligence, it's hard for me to think about. But in terms of, if what we mean by machine learning is, I mean, we could, I guess one question is, are we thinking of it in terms of like a supervised learning task? Or are we thinking of it as like, how narrowly? But I have a better idea what machine learning means than what intelligence means.
Right.
Let me inject a little historical thing. So, actually, to address this issue of intelligence. So, so you have Maxwell introducing the daemon, and then Kellen comes along and sort of interprets it a bit more, in fact, labeling the construction a daemon. And there's really Szilard at the end of his paper. He uses the word intelligence. So when we say intelligence, looking at those systems, these information engines, we're actually giving a quantitative definition to what Szilard said, because he has this construction. In fact, there's this nice weird paper 29. It's got 3 different kinds of constructions for these demons. And his whole point is Maxwell's paradox is only a paradox because Maxwell didn't tell you how to physically implement the demon.
Yeah, right.
As soon as you do that, everything is fine. And then he gives these different constructions. In fact, there's still more stuff to pull out of his paper. Like the last couple sections are really interesting. He's actually talking about what is information. And so anyway, it's just, we're actually being pretty concrete here, although if you listen to the vocabulary with the modern sense, it tells you, well, we don't know yet. But in terms of them, the early guys, using the word intelligence, we did such a complete analysis of Szilard's engine, and we gave a quantitative definition to how it worked, and that was the statistical complexity. So we actually measured the intelligence. Quantitative. So
You could call statistical complexity a measure of intelligence. That's a hypothesis. I wouldn't be committed to that because there are many definitions of intelligence you might use.
So I'm wondering a bit of if this is how you're thinking about it, or if maybe just if it's a valid way of thinking about it, that like any predictor has some capacity to predict, which bounds the amount of energy it could extract. And so if you had many of these in parallel, it would be something like an algorithm. If it was like, if you require energy to, say, reproduce, like maybe evolution is some form of machine learning that you're good at predicting therefore you win.
Yeah.
Things like you. So are you thinking about this as kind of maybe an evolutionary algorithm or just like a soup of predictive models?
Yeah, I think that was part of the motivation of this picture, is to imagine like, you know, a bunch of these engines operating in some primordial soup, and the ones that are able to propagate their information are those that have harnessed the most available free energy. You know, cells that don't eat die, and they don't reproduce. But, you know, there's a ways to go before fully understanding how this connects with a fully biological picture, for instance.
Yeah,
and
I guess like for one thing, this is assuming something about like energy degeneracy of all this stuff, right?
yeah, I mean, what we're basically assuming here is that each of these engines is designed to be as efficient as possible for its input, expected input distribution. So it's basically like a quasi-static transformation of energy, right? That's infinitely slow, and so there's a lot of trade-offs there. Practically, life happens in finite time, etc. So there's a lot of things that you have to manage.
But there's a conceptual bifurcation here. So the way you presented it,
Yeah.
you can really just think of what you're doing mathematically is talking about average case homograph complexity. So that's a whole direction to take this.
I don't Kolmogorov complexity. I mean,
Yeah.
these are stochastic.
Average case.
Average case.
Okay,
So
maybe I
you
don't
see-
know.
Well, I mean, homograph complexity is the length of the shortest, universal Turing machine program that generates the object you're interested in. Now, just look at a bunch of realizations, and then that takes you to competition mechanics.
Mm.
Average
Oh, I
case
see.
would be HP rate, basically.
Yeah.
Okay,
Yeah.
gotcha.
Yeah. So I'm just saying that's what you're stating here is actually, I think, the point I want to make is that they're really interesting questions that still need to be pursued. You're kind of giving some problem statements. There's more stuff to figure out here.
So, question session, I think a success. I would like to go forward and hit a few more notes before I wrap up, and I don't want to take up too much more time. I think we've got about 15 more minutes. So the basic idea here is basically density estimation. Estimating probability distribution over strings is the task at hand. And as it turns out, maximizing thermodynamic resources allows you to do that if you're given a certain type of machine. You know, an efficient machine specifically. Efficient machines are guaranteed to behave in this way. And if you do this, you can look at things, you just can go through it numerically, and for different size memories, look at all the different machines and look at all the different possible epsilon machines, and therefore, based on some string that you're training on, from from say length 0 to 100, you get some work rate out through trading. In the blue case, this is length 3 memory. In the purple case, this is length 2, and the red case, that's length 1. You'll notice that each of those lines lies atop any line that has a smaller memory. That's because any epsilon machine of a larger size can represent all machines of a smaller size. So that means that you can always make better predictions with more memory. However, if you were to look at the testing work rate, so after you've trained, you just feed this daemon infinite bit sequences from your original training source. You'll find a different sort of behavior where, so these regions, as I've plotted them, this is basically work production or exponential work production. This region here is where the engine is producing no work. From here to here, the engine is producing work on average, and from here above, you're violating the second law of thermodynamics, where you're producing more work than is physically possible from your available information pool. And what you see for one state memory is that you quickly learn something about your input sequence, and that you basically learn its bias, because this is basically maximum likelihood estimation. This probably reflects a statistical fluctuation in the symbol frequency. Down here is infinite dissipation, where the machine receives some information that leads it to believe a model based on frequentist data that is divergently bad for predicting outcomes, meaning that it has there's some word in your input distribution that occurs with zero probability in your inferred model. And you see that happens for a while, but then eventually you get enough statistics with 2 memory states that you pop up and you start predicting well, and then at some point you learn something new about the features and you're doing better than the 1-state model. Then with 3 states, you're doing divergently bad, breaking your machine, and then pop, you learn something about the higher order structure underlying the process. And then you actually do very well altogether, almost perfectly predicting the process. And this is basically a familiar diagram for, overfitting. The more memory a machine has, the more model parameters, in essence, and the more that it can also overfit and therefore, say, predict structure where there is none. So, in addition to doing maximum likelihood estimation, we can also think about generalizing. We can think about how do we avoid this overfitting? And in this, we recognize, okay, well, in training, maybe there's some cost to initializing a model, initializing an engine that is able to predict. And maybe the more complicated, the more complex it is, the more difficult it is to prepare. And so basically, there's a work cost to preparing this model. There's a parameter here that we basically set to be either 0 or 1 to compare different cases. And in addition, the ability to set a unique start memory state for your model is a way of being sort of overly predictive. So we choose to have an initial distribution that's either a delta function or uniformly distributed. And what you see is that pure MLE, where you're delta distributed, you have no complexity cost, you have really good training work rate, but the testing work rate is divergently bad in many cases. So this circle represents the variance of this scatter plot. But if you include both the regularization through a dissipated work in order to initialize the model, as well as give a random initial distribution, you get this plot cluster of points here, where for many training cases you don't produce that much work in training, but you actually produce quite a lot in testing, meaning that you've learned a lot of structure in your model. These 2 cases are basically just implementing just one of these regularization strategies, and they do a little bit worse, each of them, but they're still interesting to consider.
Was that the circles popping above the second law? Is that just graphic, or are there actually?
That's just the variance of
Yeah,
the
there's no-
distribution extends beyond it, but there are no points above. It's a good question, though. So you can look at this as you increase training length, and you see for the unregularized case, basically for more memory, you have really divergently bad predictive capacity. But when you regularize, you see that the predictive capacity very quickly starts to discover features of the model and not, dissipate very often. After just like 100 simples, you start, really learning the structure underlying the model pretty well. So, this is all about doing MLE or doing inference, or basically what we've shown here is that physical principles lead to a decent form of machine learning over predictive models. And as it turns out, predictive models seem to underlie LLMs. So, LLMs are basically have gone through a revolution. Maybe the revolution's over, maybe we're still in it, because of the development of a transformer. And this network of interactions and layers is somewhat difficult to parse. But the work of Adam and Paul has shown that underneath the hood, inside the mind of this LM, appears to be sort of this fractal causal state structure that is determined by an epsilon machine. So, they have this base model here, which has this causal state structure. And they look at the residual string, and they see that this causal state structure actually starts to emerge. I hope I'm not describing your work. This causal state structure exists inside the mind here. So maybe what we're seeing coming from both directions is that there are physical principles underlying computational mechanics, predictive models, epsilon machines, and on top of that, this is ultimately what has been doing the legwork beneath the hood of our most effective prediction engines, because that's what they're doing. They're prediction engines. They're predicting processes.
I don't know if we know that yet. I don't know, not to, because this isn't not a language model. This is a toy model. What you guys found. So
Right.
I guess we don't. I'm not sure if we know that there's these sort of things in like GPT-4.
There's more work to do, certainly.
Yeah.
This is preliminary.
I think what we showed is basically like this is the answer to pre-training if you do a very good job at minimizing loss.
Yeah,
Um,
but it might not be possible on like real language.
Yeah, like a lot of work to do for sure.
Yeah.
Yeah.
Not. I think it's really cool. I just
Yeah. No, I mean it's fair to point out that there's a lot of unknowns of what's actually going on in these big frontier models.
Right.
There's reason
And
to
these are
expect
data
that.
abstracts, right? We use epsilon machines in other settings to talk about the complexity of various materials and transport properties, electron material transport.
Right.
So the epsilon machines have a lot of physical and biological relevance. And Sarah's not here, but she's even showing when you look at human psychological behaviors, there is an okay approximation for certain kinds of cognitive tasks that the epsilon machine describes. So even for human things, these models, but they need to be generalized, and Alex will talk a little more about infinite memory models.
Yeah.
So,
Well, they seem very general, and also just in terms of what this circuit is doing. I mean, it's basically creating a prediction of the next token based on the history, and that is pretty much characterized by a predictive model. So I just want to run through basically how you derive this thermodynamically really quickly, because this is kind of the direction where I start to have uncertainties and not quite know where to go. So if you have some symbol sequence with the past and the future, you might apply some computation to the past that transforms it to an output and a memory state, right? And if you insist on building an energy harvester that fully randomizes the output, that reduces this 4-variable information diagram that describes these 4 random variables to a 3-variable random information diagram.
What's Y versus R again?
R is the memory of the daemon, Y is the output sequence.
Thanks, yeah.
Good question, thanks for asking. And then implementability basically means that in order for this thing to be able to implement the transformation, this local transformation has to be equal to the global transformation. You can't have any dependence of R naught on X naught, and that's captured through this mutual information being 0. So look at the information diagram, put a 0 there. This is the mutual information between the memory and the future given the past. All right, step 1. Step 2, entropy production. So we have 2 systems at 2 different times, time here and time here. There's a mutual information at time here, the initial time between the past or the future and the past, and then a mutual information between the future and the memory here, basically, because Y has no correlation with anything. And that difference, because this is a local operation, corresponds to entropy production. That's sort of irretrievable loss that cannot be harnessed as energy. And so if you need thermodynamic efficiency, if you need this to be 0, that means this mutual information between past and future has to be captured by the memory, and that basically means that this information atom is 0. So you have a predictive model. It could actually extend out here a little bit and have some random information that's uncorrelated with anything, but that would be pointless. You can basically draw it in this way.
Is that the nostalgia?
What the nostalgia? Oh, this piece
That
here.
little moon?
That's the crypticity
Oh,
in
it's
some
the crypticity.
contexts. I don't know nostalgia.
Gavin was on that paper with nostalgia.
Oh yeah.
Yes.
Yeah.
So you have to answer that.
And I don't recall.
Because you discard your nostalgia.
I think it was basically. I think it was
Things
basically.
you don't need.
I think it was basically crypticity.
I thought that
Crypticity.
nostalgia was this whatever you got in your memory that tells you about the past that doesn't have any predictive power for the future.
Right. Yes, and that corresponds to dissipation. It's very similar to this. In this case, though, this doesn't correspond to dissipation. It will in another case, though. But good identification. It is very connected. It's a little bit different. That setup's using a bipartite assumption. This is using an assumption of Hamiltonian isolation, but basically coming to the same result. And so basically, this is a way of deriving prediction from thermodynamics. But then here's one of my big questions.
Friston.
Yeah,
What?
Friston.
Carl
Oh.
Friston.
I thought you were the other author of Barley.
Yeah. So this seems to sort of be echoing Carl Friston's arguments that you should be maximizing free energy extraction from the environment. They minimize their surprisal. I don't really trust all of the thermodynamics there, but there's a large community that sort of embraces these ideas as sort of an information theoretic way of, say, training agents.
It's sort of within neuroscience, I would say.
It's true, but I think there's also
Well, it's flicker seem to avoid. Sorry.
there's also an embrace of it in sort of more of the machine learning side. But my question is really, should we expect this to happen? Should we expect thermodynamic resources to be optimized approximately? I mean, Prigogine argued for entropy minimization, but there are many counterexamples to this. You can draw basically any 3-state Markov process and calculate its necessary entropy production using the Crookes fluctuation theorem, and you will find that it is not minimal. Most likely, it is most likely not detail balanced, but nevertheless, some papers by Jeremy England have shown that you actually do see this tendency for the work production of a system to sort of reduce in general when the signal driving it is switched, which suggests this principle of dissipation, not minimization, but reduction. That systems naturally self-organize to learn something about their environment to minimize the amount or reduce the amount of entropy they produce. Specifically, this is something that he observed in complex spin class lattices. So it seems to be a property maybe of complex systems. So this is a question. Yeah.
Oh no, I was just excited about that eye diagram.
Oh, okay, yes. Eye diagram. Another place I'm curious.
Let me just make one self-aggrandizing point on the previous thing.
Right.
So there are these various groups, even over many decades, trying to find sort of the analogs of thermodynamic principles that apply to learning, generalization, and so on. So Adam Roop and I have a paper that's fairly extensive historical critique of these, including Prigogine, Haken. There are all these Friston proposing these various thermodynamic principle analogies to try to describe learning. So go there for the critique. There's a lot of, at least in the world of nonlinear dynamics and pattern formation, Prigogine's the main one who's cited for a thermodynamic principle of why organization spontaneously merges in pattern-forming systems. We go through and critique that pretty completely. So anyway, if you want, it's last year, just a pure physics report.
Yeah.
There's many cul-de-sacs have been put out over the last 3 or 4 years, and you can save yourself a lot of time.
Right.
It's just looking at that paper.
I have looked at the paper and I would recommend it to all of you. Yes, it's a good critique, but I would also say to me these are still very unknown. Like why do we see this tendency for reduction of entropy in complex systems and
this is also like a property of really simple systems, right? Like if you have just a ball sitting in phase space and you put a spring somewhere, and it's a dissipative system, it will dissipate to the bottom and dissipate more energy than the next time you put a spring because it's right close to there, even if it's dissipated a little bit away, right? So it's like systems respond to forces, and when they do that, they go to the lower energy states. So this feels intuitive to me and not necessarily indicative of anything complex.
we should discuss. I'm realizing we're coming to the end of my time here, and we started a little bit late, but not so late that I should go much further.
We're basically at 50 minutes.
We're at 50 minutes right now? All right, well, in that case, I will just share one of the big questions I have is, okay, if this is a framework for deriving predictive intelligence, what happens when you expand the diagram to think about not just things that harness energy, things that create structure, transform structure. And for that, you need a more complete 5-variable information diagram. So this is a toy I want to encourage you to play around with and see, can you, by setting things to be 0 and forcing new conditions, looking at this transformation, new conditions like implementability and efficiency of that transformation, can you arrive at new conclusions about how to transfer information?
Quick technical question about that. Does that kind of diagram include all possible atoms you could
Yes,
have?
we have 2 to the 5 minus 1 atoms.
Yes,
So what he's doing
rated
is
this
trying to
very
draw
Did you really
precisely.
do that so you could get all the atoms in there?
Yeah,
Oh,
I
yeah.
didn't know that was possible.
Yeah,
for
we-
5.
But
6 it's hard.
6 you can do it, but it's really hard.
Yeah.
Really? Okay,
Yeah.
interesting. All of that offline, Austin.
I want to see the 6.
I don't have it on.
Yeah, but then there are no
I think I have a
planar
photo
representations
somewhere.
of the eye diagram, and that makes it really hard to use your visual
So
information.
Sorry, I really want to wrap up
Yeah,
here.
sorry,
There's something I really want to say
No, you do.
because it's weird.
Okay.
Okay, so predictive intelligence is something that you can consider in this context where you think instead, okay, rather than my outputs being totally random, my inputs are totally random. And what you wind up with is basically a time reversal of your original picture, where this idea of nostalgia is actually a cost. This is where you see the same thing, where this sliver is basically going to cost you energy. And so the memory of the daemon winds up containing features of the future. It's like having a plan. It's thinking, how am I going to make this music? How am I going to build this airplane? How am I going to, I don't know, finish my talk. I feel like I'm transforming more than I'm generating at the moment. And as it turns out, AI structures that are built for generation, like Josh Hissel, Dick Steen's really groundbreaking thermodynamic derivation of, a way for generating structure. It's the basis for DALL-E, it's the basis for a lot of image creation, is basically time reversal of diffusion. So it seems like there's an intuitive connection here. So I would argue also for doing information diagrams with interacting agents where this becomes a much more complicated circuit diagram. And I would speculate that a purely predictive intelligence is extractive. It's consuming resources and destroying structure. So if we're focusing all the time on predictive engines, maybe we're dooming ourselves to the robot death. Maybe what we want from an AI is something more retrodictive, more generative, something that creates structure, opportunity, beauty, rather than just recklessly trying to, identify as much predictability in its environment as possible. So, thank you for bearing with me. I would like to thank my co-organizers and, the Federation of American Scientists, which has empowered BITS to, host this workshop. So, thank you.